So I hope I'm audible. Let me just present my screen. Is the presentation visible? Yes, sir. Yeah. So let's start our session for today. So, good evening, everyone. Welcome to the week 6 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasanajit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, Assam. I am responsible for conducting the weekly live interaction session for this course. So, we have come across five live interaction session. 5 weeks of the 8-week course has already been completed. So, with the last week, we concluded our discussion on the thermal conversion routes. So, we discussed about different types of thermal conversion routes. So, as usual, I hope everybody is now familiar with those. So the first one is your gasification, pyrolysis, and then incineration, or you can also call it as combustion. So we discussed the fundamentals of each. We discussed on the more than me saying myself discussing, the course discussed on the different the process flow sheet, the application of these three different processes in the real life. So after that, last class we discussed on something so called as energy conversion from plastic waste. So we use the pyrolysis process as a basis for converting the plastic waste into some form of the energy. So there we discussed about, so starting from the fundamentals, we discussed on what is polymer, what are the different kinds of polymers, and in real life application how the polymers are typically used, what are the different kind of polymers that are used in everyday application. And then we discussed on how to convert this plastic waste into different forms of energy. So there we discussed about thermal pyrolysis, and also we had discussed something so called as catalytic pyrolysis, where we discussed about how the use of catalyst reduces the temperature of the pyrolysis reaction. Like typically pyrolysis happens at a temperature greater than 1000 degrees Celsius, and how it can be reduced using this catalytic pyrolysis process. Then we discussed about how the fuel quality gets improved, and how the cost of the entire pyrolysis process gets reduced. We also discussed about the various factors affecting the pyrolysis process of plastic waste, and we discussed on something so called as gas cleanup. So we discussed why the gas should be actually cleaned, or why the particulate matters and other sorts of harmful gases should be removed before the gas is let out into the atmosphere. So we after which we discussed about, so basically in that gas cleanup we discussed about removal of particulate matters. So there we discussed about around 3 to 4 different ways to remove particulate matter from your gas. So can anybody remember what are the 3 or 4 different methods for removing particulate matter? So these are like some sort of the equipments that I'm talking about. Yes, anyone? Yes. And then we discuss something so called as ESP, electrostatic precipitator, cyclones, and fabric filter. So, yeah. So each one of them basically works with a different principle, as we discussed previously, that your gravity settler uses the gravitational force as the main, uh, you know, gravity force as a main mechanism for removing the particulate matters from the gas. But however, we also discussed about the disadvantage that it can remove only the particles which are greater than 50 micrometer in dia. So any particle which is lesser than that, or more fine particles to be speaking in general, cannot be removed using this gravity settler. And then we discussed about the electrostatic precipitator. So over there the main principle was the electrostatic force. So you have two collection plates. Is it possible to, let me check, five, yeah. So we discussed something on this electrostatic precipitator, where we have the collection plates, and in the space between the collection plate you have a discharge electrode. So once you pass the gas, sorry, you apply voltage, and then this collection plates acquire a positive voltage, and then the discharge electrode has a negative voltage. So when you pass the particulate, when you pass the gas, the particulate matter in the gas basically gets negatively charged due to this discharge electrode, and these gets attracted towards this collection plate which are positively charged, and from this the, and due to this electrostatic force between the positive as well as that of the negative charge, the particulate matter in the gas gets removed from the gas, and it gets collected on the collection plate. Once the collection plate is covered with the particulate matter, it is disconnected, and then it is cleaned up. After that, we have the cyclone. So cyclone predominantly uses the centrifugal force of action as the main mechanism to remove the particulate matter from the gas. After that, we have something so called as a fabric filter, wherein the fabrics are used for removing the particulate matter from the gas. So it's something more like a filtration technique. So we discussed, I guess, up till there. So, and that particular week we concluded on the thermal pyrolysis technique, or in general the thermal conversion routes for energy production. So week 6 is something where we will be starting our discussion towards energy production from anaerobic digestion, or more specifically speaking, the energy production through biological conversion routes. So that's what is something which I have given it in the form like as a comparison. So in the thermal process, you have the biomass. The biomass is burnt either in the excess, or excess supply of oxygen, or limited oxygen, or in the way, in the, what do you say, in the absence, or in a very deficient amount of oxygen. And we have these three different type of processes. In case of the biological conversion routes, that's what something we are going to discuss today. So the first one is the anaerobic digestion process. So as such, when you say about anaerobic digestion process, so the process is nothing but it's a sort of a digestion process wherein your biomass, yes, yes, you are asking for anaerobic, right? Anaerobic, that's what. So it usually happens in the absence of oxygen, or you can say very limited supply of oxygen. Is that okay? So here it's a digestion process. Okay, yeah. So here it's a digestion process is because this biomass, which is a complex compound, is broken down. So since a bigger molecule is going to be broken down into simpler substances, we call this as a digestion process. And since this digestion process happens in the absence of oxygen, or very, very deficient amount of oxygen, This process is called anaerobic digestion. So the difference between anaerobic and aerobic is basically the presence or the absence of oxygen for the digestion process. If the digestion process uses oxygen, then it is called as aerobic digestion. So that is something that what happens in humans. So the food that we eat gets digested. So the one that so that is what is going to be produced in the form of energy. So in our case, we are something like more often for us it's a aerobic digestion, but here the biomass is getting converted. This particular process happens in the absence of oxygen, called anaerobic digestion. So this anaerobic digestion process, which happens on the biomass, basically results in multiple compounds, or you can say multiple form of products. So one is the biogas. Apart from biogas, you can have hydrogen, then you can have compost. So anything else apart from biogas, hydrogen, compost? Yes, different forms of or different products of the anaerobic digestion of biomass or this waste material, organic matter. One is the biogas, so that is going to be a main component. After the biogas, you have is the hydrogen. After that, you have something so called as compost. Then apart from that, anything anyone is able to remember, because there are, if I am not wrong, there are more than three. Yes. No. Actually, I'm asking what are the different type of products that gets generated during this anaerobic digestion process. Like you have biogas one as the one product, hydrogen gas is the next one. Even though it is generated in a limited amount, but yes, that is also one of the product. After that, you have something called as compost. Then apart from that, do we have any other products that we get from this anaerobic digestion process? Yeah. Vertical. Yeah. Yeah. So reusable water. So that's a good point. Where will I write that? So first one is the biogas. So that is the main component. Then you have compost, hydrogen gas. Then you have reusable water or recyclable water. What you can say. Then apart from that, anything else anybody is able to remember? So this is fine, but I guess we have one or two more. So I hope it is better that anybody like if I actually suggest everyone to look after this, because this is actually one of the most commonly asked assignment questions also. So they usually ask what are the products, or which one of the following is the product when the biomass undergoes anaerobic digestion process. So it's better to have all the five things in mind, so that it will be easy during the assignment sessions. So so as somebody said that residue is nothing but, so once the digestion process happens, there will be some sort of a residue that will be going to get generated, and that residue is nothing but is can be used as a compost, or it's like can be used as a fertilizer for the agriculture purposes. So if you see in case of this biological conversion routes, the percentage of solid content is very less. So it's if I am right, then the percentage of the solid content is going to be only 8 percentage. Whereas so the rest is nothing but it's going to be water. The 92 percentage of the component in your biological conversion rule, that slurry that you prepare by mixing the solid content and the water, it has only, that slurry has only solid content of around 8 percentage, but the remaining entire is water. But in case of thermal conversion routes, that's not the case. Over there the solid percentage will be more, and we actually want a material which has more solid percentage and a lesser moisture content or water content. So here I want to ask a question, why is that so? So like in case of the thermal conversion routes, why do we want to have material which has higher solid content, or which is particularly very what do you say, dry, and not we do often don't prefer a wet sample for the thermal conversion process. So, any idea on why is that so? So, in order for you, so that moisture will actually inhibit the thermal conversion process. So, the amount of energy that is actually required to burn your material is going to be significantly higher. So, the fuel that you are going to add to basically burn or to yeah burn your material is going to be more. So that is something that is energy inefficient, because the amount of energy that you're going to give into the system is going to increase. So that is the reason for the thermal conversion routes, as somebody rightly said. Now we prefer a sample with more solid content, or basically a sample which is having very less amount of moisture in their system. So after this biogas is the main product, as we said. So the biogas composition is predominantly going to be your methane and carbon dioxide. However, it also has other components. So one is your nitrogen gas, hydrogen gas is also going to be produced, oxygen. Oxygen, and sometimes it is going to be your hydrogen sulfide. However, these components, that is your nitrogen, hydrogen, oxygen, as well as the hydrogen sulfide, dihydrogen sulfide H2S, is going to be present in minor component. So here let me ask one more question. So if you see in this case, you have let's say N2H2O2 and H2S. So only if you consider these three as your component, because this biogas will be getting utilized up. So if you see this nitrogen, hydrogen gas, oxygen gas, and hydrogen sulfide, if you are going to emit this gas out in the atmosphere, which gas should be removed before it is let out in the atmosphere? This is something that we learned in gas cleanup. So just evaluate only with respect to this. Among these four, nitrogen gas, hydrogen gas, oxygen gas, and hydrogen sulfide H2S, which one you need to remove before you leave this gas out in the atmosphere? Hydrogen sulfide, because it is harmful to the atmosphere. So yeah, that is fine. So talking about this biogas production, the amount of biogas that is going to be generated typically depends upon the property of the biomass material that you take. So it's not going to be directly related either to your average dry matter content, that is the amount of methane that is going to get generated, or the biogas content that is going to get generated, does not typically depend upon how much the sample is going to be, dry. So it is going to depend upon the amount of it is going to depend upon the material properties of the system. So for example, if you see the chart in the coursework content, in the course content, so you can see that there are some material which has high dry matter content, but they have lesser biogas content in them. So this amount of biogas that is going to be generated by burning or by this anaerobic digestion of the biomass typically depends upon the material property, or typically depends upon the nature of the biomass, rather than other what do you say rather than the other physical parameters. So let's keep this biomass conversion up to here, and let's move towards this fermentation process. So the second process of this biological conversion route is going to be your ethanol fermentation. So here you're going to use some sort of the bacteria, or you can say fermentation bacteria, to convert your sugars into alcohol plus carbon dioxide. So this is one of the examples. So you have your C6H12O6. I hope everybody knows what is C6H12O6, the general name for it. Sorry, the general name for it. Yeah, glucose. So this glucose, when it undergoes this anaerobic digestion process with the help of some sort of a microorganism, like for example, in case of this hexose or that glucose, whatever you see, if you use yeast as the microorganism, then under this anaerobic digestion process, you are going to end up with ethanol plus carbon dioxide. So this ethanol is going to be used as an energy fuel in it is basically used as an energy fuel in your vehicles and other systems. So this ethanol, what you are going to do is you are going to actually mix it with gasoline, and that one is actually going to be used for your is actually going to be used in your vehicles and other kind of places where you going to use fuels for the energy production. So there is a question here. I have stated that the ethanol should actually be mixed up with gasoline. So if you see, in case of, if you take for example, instead of glucose, if you take other high molecular what do you say sugars, let's say fructose or sucrose or more, or something which is more which has higher carbon, or which has higher saccharide units, or high, or like you can say complex sugars, you're going to end up with a higher alcohol content, something like butanol. So this butanol as such can be used for your what do you say can be used as a fuel directly, or it can be mixed up with the ethanol. However, in case of ethanol alone, you cannot do that. You need to actually mix it with gasoline. So can anybody try to relate why is that so? Like in case of butanol, you can directly use it as a fuel, whereas in case of ethanol, you actually need to blend it with gasoline to be used for this energy production, or in case of the vehicles. Any guesses on why is that so? Okay. Other than that, like why ethanol is blended with gasoline, whereas butanol, it can as such be used as a fuel, or it can also be blended with ethanol, but ethanol does not have that what do you say a property of being used as a fuel by itself. One of the reason is the amount of energy that the ethanol carries. So ethanol carries lesser amount of energy compared to butanol. So because of that, it needs to be actually mixed up with the gasoline so that it can be used in these vehicles, and yeah, so that it can be used for the energy production in the vehicles, or like it can be used as a fuel for vehicles. So that is one of the reason. Apart from that also there are certain reasons. So if anybody is able to guess, then it's fine, or I would suggest everyone to actually look up this in the internet. I will mention this as a question. But if you have any guesses on this, apart from the energy point of view, you can let me know. Any, it can be a wild guess. So it need not be. Okay, as such, I'm giving this as a question so that everybody can look at it and come to know. So, in this fermentation process for the production of alcohols, it need not be only ethanol; it can also be butanol. However, they talk about ethanol and butanol. What about that in between compound, something called as propanol? Why? I mean, can that be also be used as energy fuel, or does it have any kind of limitations? So ethanol and butanol, every one of us know that it can be used as a fuel. But what about the compound that is in between these two alcohols? What about propanol? So I'm going to add that also as a question. What about propanol, phenol as a fuel for as a fuel? Do we have space? So I would like as recommend or suggest everyone to actually look up at these two questions, because it could be interesting. We might end up with knowing something which we may not be aware of previous. Because if ethanol and butanol are going to be used as fuel, then what about something that is in between, so called as propanol? So, in this ethanol fermentation process, you have multiple steps for production of ethanol itself. So, you have something so called as pre-processing, then you have something called as fermentation. After fermentation, you try to concentrate the ethanol, and after that comes your dehydration step. So, only in this, so the reason why this dehydration step is required is basically to make sure that the ethanol is anhydrous in nature, so it loses all its water molecule, so that it can be actually blended with your gasoline. So that is the only purpose of using additional step of dehydration, wherein you can make the hydrous ethanol to a form of anhydrous, and then it can be blended with gasoline so that the calorific value can be enhanced, so that the energy so that it can produce more energy, so that the process can be more energy efficient. So there are also few more processes, but we have questions as such which is there for us to discuss. So we will discuss about these two processes more in detail when we discuss about that question. Now we come, yeah, yes. So propanol is used in the Indian oil. Okay. Okay, yeah, so that's what. So, it is better. That's the reason I'm going to give it as a question here for everyone, so that, to look up what is the use of propanol or how is the prospect of propanol as a fuel, as an energy fuel here. So let's discuss about this in the, yes. Okay, 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 okay. Okay, so yeah, so let this be a question for others. Let others also, check, and let's discuss about this in the next class. I'm going to mark it here. So you say that so as per the ethanol is also sorry, propanol is used in the Indian oils, right? Someone said just now, I believe. Okay, so let it be here and let's move towards something called microbial fuel cell. So this is a very, kind of area which is gaining interest. So lots of work has been done on this, but again, this is something that has been, of interest to researchers in the recent days. So in the last 20 years, this has been of greater interest to many of the researchers, especially the people who are working within this energy production or energy storage side. So let me just ask a question. So is there any one of you who is attending this session who works on this particular topic of microbial fuel cell or fuel cell? Anyone here? Okay. So so let's start with the discussion of a fuel cell. So the fuel cell is nothing but it is a typical galvanic cell. So which uses, what do you say, the free energy of a chemical reaction, and that gets converted to a electrical energy. So as such, the definition of the fuel cell goes as a fuel cell is a cell where the chemical energy is converted into electrical energy. And when this particular energy conversion, that is your chemical energy to electrical energy conversion, happens in the presence of microbes, that process or that particular type of cell is called as a microbial fuel cell. So in case of a normal fuel cell or a hydrogen fuel cells, you will have the hydrogen gas in the anode side and oxygen gas supplied through the cathode side, and then the reaction happens. In case of the microbial fuel cell, the difference is that the instead of supplying hydrogen gas directly into the fuel cell system, you are actually going to feed the anode chamber with bacteria and organic matter. So these bacteria are going to actually act upon this organic matter, and then that electrons will get generated. That electrons as well as the protons will get generated, which will be used up at the cathode for the production of water. And that electron that gets generated in through the process goes to the load, and over there it what do you say, delivers its energy or expends its energy and then moves towards the cathode. So, yes, yeah, yes, that's correct. Excuse me. Uh, it can be, but again, so that depends. In this, I'm not very sure whether it can be used in the wastewater. But again, if you are going to use that, it it is typically with organic matter. So, in case of wastewater, it depends upon the, what do you say, that sludge that is going to come with it. So, do we have enough space here? Okay, let me go with the new slide. So let us write the reactions actually. So that is more important here compared to the, because mechanism is based on the reaction only. So yeah. So let's first discuss for the fuel cell before we go for the microbial fuel cell. So you have anode. So can anybody tell me what kind of chemical reaction happens at the anode? Is it oxidation or is it reduction? So always at anode oxidation reaction takes place. So you have the, in case of your hydrogen fuel cell, let me write that also. Hydrogen fuel cell, yeah. So here you will be supplying hydrogen gas to the anode chamber or to the anode, and that hydrogen gas will be converted to H plus electrons will get generated. So this H plus will be transported through the membrane. So if you see here, this is the membrane that we have. So that H plus ions, whatever is going to get generated at the anode, will cross this membrane or will move across the membrane or travel across the membrane, or you can say permeate across the membrane and move towards the cathode side. So in case of the cathode, it is the reduction reaction that is going to happen. So in case of the cathode side, you will supply oxygen, and then this hydrogen gas that is going to permeate across or travel across the membrane will also go for this reaction. And then the electron also, once it goes through the load, it expends its energy on the load and then it moves towards the cathode. So these, all these three components are going to react with each other to form H2O. So it is 2OH minus actually. So it will form OH minus ions. So the entire reaction, when you are going to write, when you are going to sum up the entire reaction, you are actually going to get water. So if you sum up the entire reaction, then this H plus and electrons will get cancelled out, and then you will have this, wait, am I okay, sorry, it will give H2O. Just a second, once a second, 1 minute. So okay, so you are going to get H2O. So that H2O will come out of the cathode, will come out from the cathode side. So this is in case of your hydrogen fuel cell. So in case of the microbial fuel cell, can anybody tell me how the reaction will change? So in case of the anode, you are actually going to have your organic matter that is going to be present. So let's consider that organic matter as, let's give this as a general, empirical form of the organic matter. The empirical formula is CXHYOZ. and then you will have the water molecules also going to be present. So these two, yes. Screen is not visible. Okay, just it's not visible. Okay, okay, just a second. Let me, what do you say? Stop presenting and present again. So then we will see. What about now? Is the screen visible? Okay. So this will give carbon dioxide plus your proton plus electron. Again, this proton is going to pass across or permeate or move through across the membrane towards the cathode side, and it's going to react with the oxygen there. So it will be something like this. Again, I'm going to write here the empirical form so that it can be generalized for any kind of organic matter that you're going to take under consideration. This will give rise to water. So this is up to the microbial fuel cell, and in case of this anode, you will have some sort of microbes which will be used as a sort of a catalyst, or it will act upon this organic matter, generating carbon dioxide as well as electrons. So here, so in this case of the fuel cell, two things are going to be you're going to actually get from this process. One thing is the energy that comes out from this redox reaction or the chemical reaction. Energy will be produced, so that can be harnessed. And then the second one that you're going to get is the water molecules, H2O. And this water molecule is the purest form of water that you can actually get from this particular process. So these are the two products of the fuel cell fuel cell energy generation process. So here what happens is, again, as such as every single process is concerned, this process also has typical problems associated with them. So one of the problems is that the electron transfer. So here that electrons that are going to get generated by the bacteria's by the digestion of the biomass or by the bacterial action of the biomass, that electron actually needs to be transported to the anode surface so that it can be taken to the cathode. So this anode should actually collect that electrons that get generated here, and then this electron should, and then through the anode only the electron will actually move towards the cathode. So in order for this transfer process to happen, sometimes there are chances that the bacteria that you're going to use may not directly transfer the electron to the anode. So there are two different processes. One is the indirect transfer process and another one is the direct transfer process. So depending upon the type of bacteria that you use in this system, the mechanism for this direct or indirect transfer is going to change. So can anybody tell any example of a direct transfer bacteria or direct transfer microbes which is used in this microbial fuel cell process? Direct transfer microbes. Yes, any ideas on direct transfer microbes? Any examples? Yes. Okay. So another one common example for direct transfer is your E. coli bacteria. So E. coli, that particular microorganism is like E. coli is a very commonly known example. So if for me the first thing that comes in my mind for a direct type transfer microbes is E. coli. But again, I would suggest everyone to look at those slides for the biological name and try to have you know, like try to keep in mind at least one or two, so that you know it will be easy. Or it will be, you know, sometimes there are chances that they might ask one of the name of the bacteria, so at that in that case it would be helpful. So here, if you see the components, we have to discuss about anode. So as I said, anode is nothing but the place where the oxidation happens. Cathode is the reduction happens. So typical materials for the anode and cathode is graphite plate is one of the best material. So the basis for choosing the anode and the cathode materials as graphite is basically because of the electrical conductivity. So they need to be able to be you know, conduct that electron and transfer it from the anode to cathode. So it should have very less resistance and it should be highly conductive. So that is the basis for the selection of the anode and the cathode material here. Apart from that, you have something called as proton exchange membrane. So that is the PEM. So what is the commonly used proton exchange membrane in the fuel cell? Uh, Cellulose acetate. So as such as a membrane, the most commonly used one is the Nafion membrane. So cellulose acetate, I'm not exactly sure whether it can be used as a membrane material, because as such it will be a membrane. So does cellulose acetate, I mean, have you have heard about this anywhere, that cellulose acetate is used as a membrane? Because I'm not very sure about this. Polymer membrane, Nafion is also a polymer. So many polymers can be used for this proton exchange membrane. Out of that, the commercialized one is the Nafion membrane. So Nafion is the most commonly used membrane in case of the fuel cell, whether it is hydrogen fuel cell or microbial fuel cell. It is the Nafion membrane that is commonly used for the fuel cell as such. So this Nafion membrane typically works based on the, you can say, the H plus ion hopping mechanism, or there is a so-called term as Groth's structural diffusion mechanism. So let me just write that name, Groth's structural diffusion mechanism. So here what is the thing is, so Nafion as such, it is a commercialized name, so it's a common name. Oh, sorry. Nafion is a commercial name. So the chemical name for Nafion is PFSA, or you can say it as perfluorosulfonic acid membrane. Perfluorosulfonic, sorry, sulfonic acid. So why is this? I'm not sure. Okay. So PFSA, that is the perfluorosulfonic acid. So this is the chemical name for the Nafion membrane. for Nafion. So this what it has is it has a PTFE backbone, that is your polytetrafluoroethylene background, PTFE backbone, and it is decorated with the SO3H group as pendant chain, that is the side chain. So the SO3H groups are present as pendant chains. So what happens is screen is not visible. What about others? So can you? Okay, okay. So okay. So let me just try presenting. Let me stop presenting and present it again. But yeah, just let's see. Now is it visible? Okay. So I guess some sort of internet connection issue, so that's fine. So this Nafion membrane should be actually kept in a hydrated condition. So the major reason why it should be hydrated is because this SO3H group will be present as SO3 minus and H3O plus ions. So it will be in this form. So what happens is when one H plus ions from the, whatever that whatever kind of the reaction that happens, either this oxidation reaction or this oxidation reaction, when the H plus ions come in contact with the SO3 minus groups, what happens is it kicks out this H3O plus and then occupies that space, and this H plus ions or H3O plus ion that gets kicked out goes to another SO3H group that is present in the membrane, and kicks that H plus ion from there and occupies its space. So it's like it's that the H plus ions are going to travel across the membrane. So it's like a hopping mechanism. So one H plus ion comes, it displaces the other H plus ions from its side and occupies its space. That displaced H plus ion goes to another SO3 H group, displace that H hydrogen from there or H plus ion from there and occupy that space. So this keeps on happening, and at one point what happens is it gets terminated. So at one point there is no other SO3H group available, so that H plus ion at the end comes out, and that one is going to actually participate in this cathodic reaction. So it's like a H plus ion going to, it's like a H plus ion that is going to get travel, but it is not the one that is getting generated at the anode, but it comes out from the membrane itself. So that's why this mechanism is called Grotthus structural diffusion mechanism. So this is about the membrane. Catalyst, again, depending upon the process it is used. So the most commonly used catalyst, or you can say the commercialized one, is the platinum or platinum supported carbon substrate. So you have a carbon substrate and you deposit platinum on top of that. These are the most commonly used one. But apart from that, you have polyaniline, that is also a polymer which can be used as a catalyst. Manganese dioxide MnO2 is also used as a catalyst in this process. So let's move on to this question sections, or okay, let's discuss about the process that affects the microbial fuel cell. So what are the process that you think will affect the microbial fuel cell? Yes, 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 sure. Yes. Mm, 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 Hmm. Yeah. Hmm. 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 Yes. Hmm. Hmm. Yeah. Okay. Yeah. Yeah. Hmm. Hmm. Yeah. So leftover as such is like, in the sense, do you mean like whether you're asking whether water will be left over in the anode, or you mean anode? Uh, mm, yeah. Yeah, yeah, sure. Mm, mm, mm. Mm, yeah. Mm, 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 yeah. Yeah, true, true, true. Mm, 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 mm. Okay. Mm. Or you mean anode? Uh, mm, yeah. Yeah, yeah, sure. Mm, mm, mm. Mm, yeah. Mm, 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 yeah. Yeah, true, true, true. Mm, 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 mm. Okay. Mm, mm. Yeah. So it will be that slurry form only, the broken down organic matter. So yes. No, wait, wait. There is a question that is going on. So let me just first, let's discuss that question first, and then we'll discuss about the factors. So yeah, you will have the slurry also that is going to be left out, and apart from that, that carbon dioxide also will be released. So that carbon dioxide that is going to be released will be actually taken out. And if there is any form of the slurry that gets generated, because once you break down it is not necessary that all of them are going to get converted to carbon dioxide. Then the problem is with the efficiency of the process, the amount of energy that gets generated, the voltage. So as such, the electron that is going to expend its energy, we will actually measure it in terms of voltage. So ideally speaking, this water combination reaction should give a voltage of 1.23 volt. So that is the thermodynamic potential for water splitting. So when water is going to combine, it should give that 1.23 volt. However, from when it is tested, it is the voltage that you're the voltage that is going to get generated is less than 1 volt. So it typically varies between zero point 0.7 to zero point 0.9 volts. So still there are a lot of research going on to improve that particular part. So how to get more amount of energy from this fuel cell is still you can say a interesting point of research which is happening in many places in India itself. So yeah, it has lot of prospects. Mm. Yeah. Many places it's still going on because they want to use this organic matter as a ways to convert the energy. Yes, if so, NIT Trichy does work on this microbial fuel cells. So they work, and if I am correct, then even Central Electrochemical Research Institute of the CSIR branch, they also work on this microbial fuel cell. In IITs also, they do work on this microbial fuel cell. So yeah, research still is going on within this particular field. So especially what they are more trying to understand is the mechanism for this electron transfer. So that is their, yes. Yeah, that is the different type of cell. So they are used up. So yeah, so speaking from the research point of view, yes, still it is going on because as I was saying, so the predominant point of research or the interesting part is that the mechanism of electron transfer. So they want to improve that process because as you see, indirect transfer happens in many microbes as well. So they want to use different kind of mediators so that the process efficiency is improved. Yeah, so factors affecting the MFC process. So the first one is the, yeah, temperature, organic matter, the organic material that you're going to put into your system. Then you have the electrode substrates. Yes. Yeah, pH of the electrolyte that you are going to use. And then you are going to have the type of catalyst. Then, yeah, type of microorganisms. And then anything else? Yeah, uh, type of oxidant in the type of oxidant in the anodic chamber. So yeah, so these are the different factors that affect the MFC process. So let's go to the questions. So I hope if there is any doubts, you are welcome to ask me, or we can go towards discussing the questions. Hmm. Okay. Using of a membrane, yeah. So in that case, I will have to look up at that because I am not familiar with that. I mean, this is not my area of expertise. So I'll have to look up at that, and then I will let you know about this membraneless fuel cell, because I guess again, see, okay. So then what about the sort of like you can expect it as that you will get pure water. So but as such, what somebody has told, so you cannot actually derive any energy out of this process. So it's typically something more often to produce pure water, but again it would be a very expensive process to produce pure water. So yes. Water impurities, so one will be your particulate matter, which can be, you can treat it as impurities. Then another one is the hydrogen sulfide, also is one of the impurities. Okay. So again, as such, see, so I also wanted to say something is that this microbial fuel cell is an evolving concept. So research is still going on. That's the reason we come up with different types of ideas like membraneless fuel cells. So that means it is, so these are all very new things that are evolving up within the fuel cell. So it's of relevant to the research interest even these days. So yeah, so there are a lot of work which is required to be done to make sure that for different purposes this can be used up. Again, I was not very aware of this membraneless microbial fuel cell. So it's something that I would probably, see through after this session gets over. So yeah, that's something interesting coming up from your side. So, hmm. Oh, hmm. Yeah, yeah. So, hmm. Hmm. Yeah, yeah, yeah. We have a question lined up. Like after the theoretical question, we have one question related, almost very similar in statement. So, hmm. So yeah, we will come up with this within another 10-15 minutes. Yeah. Yeah, yeah. We have a few numeric what do you say, theoretical questions to discuss, and then we will come up to this question only. Okay, yeah. So the question is, the first question, as you can see, match the complex compounds and their typical hydrolysis products. So which one among the A, B, and C and D are okay? Any other answers? Somebody has told B. Answer A. So the answer is A. So option A. So here, if you see, I hope 3 and 4 are fine. So protein, so protein's basis is amino acids, and for peptides, and is this fatty acid. So 3 and 4, I hope it is clear to everyone. So if you see, in case of cellulose, the hydrolysis product will be glucose and cellobiose, and for carbohydrate it will be sugars and alcohol. So cellulose is nothing but it has many glucose units actually linked together, so it's a long chain of glucose molecules. Cellobiose is nothing but when two glucose units are linked to each other, so that is what is called as cellobiose. So let me just mention that when two glucose units are linked together, then you call that then you call that as cellobiose. So cellulose is many glucose units linked to each other. So this is cellulose. So glucose is one single glucose units. So for carbohydrate it will be sugars and alcohols. So the right option is option A. So yeah. So next question, factors affecting the biogas yield: C/N ratio, temperature, pH of the solution, all of the above. All of the above, because with respect to temperature your yield is going to change, with respect to pH your yield is going to change. The specific reason is because for biogas production, actually, can anybody tell me, okay, so here we have one question. List out the step in the anaerobic digestion process for biogas. So can anybody tell me what are the four steps? So based on this, we can answer that question. Yes. Is it aceto or acido? Okay, acidogenesis. Yeah, yeah. So the temperature becomes important because all these processes that you see are typically bacteria dependent. So your acidogenesis is going to use acid causing bacteria. Your acetogenesis is going to do some sort of a bacteria which can produce or which can lead to the production of acetic acid, and for methanogenesis you are going to use some methane producing bacteria. So when you are going to use bacteria, the temperature and the pH of the solution is going to become very important. So if you are not going to use appropriate temperature or appropriate pH, these bacteria are not going to be effective, so they will just die. So that will reduce the yield. So, or if you give very less temperature, then the bacterial growth will not be sufficient. So if the bacterial growth is not going to be sufficient, then again it is going to be what do you say, the yield is going to actually get reduced. So if you plot a curve of the yield versus the bacterial versus the temperature, it will be something more of a parabolic curve, which is parabolic curve facing downwards. So here the option is all of the above. So let's leave this question for some time. Move on to question number, the next question. Comment whether the following statement is true or false. Fuel cell is a type of galvanic cell. We just now discussed, so true. Okay. And can anyone tell me why it is true? Like, yeah, so in case of a microbial fuel cell, it's going to be microorganism, or if it's just a fuel cell, then you can just say the fuel is going to get converted to water and some form of energy. So yeah, that's fine. So then this question is also, then yeah, let's come to this question. So you have A, B, and C. You are supposed to identify what is A, B, and C. I think with the discussion we had on fuel cell, I hope now everybody will be able to identify. No, no, no. The question above that. Identify A, B, and C in the fuel cell. Answer is yeah. So you have anode for the A, and the cathode is in the oxygen process, and cat. So in case of C, it is the proton exchange membranes. So the next question, I guess somebody said fermentation, so that is correct. Okay, let's come to this question. The number of steps for conversion of matter or any kind of organic matter, let me write, to alcohol is in the following order. Now, can anybody tell, comment on the following trend? So, first of all, just for the sake of knowing, when you are going to convert this organic matter to alcohol, what are the steps that are going to be involved in general for any organic? Yes, just a second, 1 minute. Pre-treatment. Okay. Yes. So this is fine. So in case of the, so for each and every lignocellulosic biomass, starchy crops and sugar, the number of processes for the conversion, if you see, is increasing. So in the course lecture slides also you can see that the number of techniques or the number of steps for the production is more in case of a lignocellulosic biomass compared to starch and sugar. So why do you think that this particular trend is present? Any ideas? And sugar. So, so why is that so that lignin should be removed? Like, I mean, why can't you use lignin also in the conversion process? Yes. True. So it is the cellulose that is the only thing which is going to actually, contribute towards this. You can say that, for the energy production. The lignin is just a sort of like a, you can say, you can say it like something more inert, which will not be suitable for the energy production, or it will not basically contribute towards the energy production. And the reason why lignin removal basically causes for larger number of steps is basically because the hydrolysis of lignin, if you see, is very slow. So that is one of the main reasons why the number of steps is more. And if you ask why lignin should be removed, then as somebody rightly said, it is basically because it does not produce anything worthy enough, or it does not contribute much for the fuel production, or it does not carry much or add energy value to the fuel that you're going to generate out at the end. So yeah, so I hope this is done. So let's move towards this question. Any I hope all the questions were straightforward. So any things that anybody wants to share on this, or yes. Yeah. So wait. So excuse me. So just a second. Is this an assignment question? So actually, I'm not supposed to say the answer for an assignment question because I'm bound with some what do you say, regulations. So it is better that, if we want to discuss the assignment questions, then it is better we discuss more of the numerical type, and I would suggest others also to what do you say, uh, like, just try not to basically do the discuss on the assignment questions here. So I can give a clue, but I cannot directly say the answer to anyone, because that's I'm bound with certain rules and regulations wherein we are asked not to discuss any of the assignment question or reveal answers to the assignments questions. So yes. So, as such, for the numerical question, we can do something very similar to that. So, it will be a kind of, help, or like it can give you hint. But for straightforward theoretical questions, we can discuss this after that assignment evaluation date. I guess 5th March is the deadline. So, after that, in the next week, we can take up that one. Okay. Yeah, yeah, yeah. So the parameters are changed here a little bit. Yeah. So, I hope every, yes, I am not sure because I'll be solving it right now. So let me just read out the question to all first. That is the priority. So determine the volume of the digester chamber for the biogas production from the cow dung for 10 cows with a body weight of 200 kg each. Assume that the temperature is 30 degrees Celsius. The solid content of the cow dung is 15% and the HRT is 50 days. One cow produces 15 kg of cow dung daily, and consider the favorable condition as 8 percentage concentration of TS. So TS is your total solid. It's a straightforward question, so I think I will start solving it because somebody has told the answer to this question also. So for one cow, it produces around so 15 kg of cow dung. So 10 cows will produce 15 times 10, so that is 150 kgs. Out of that, 15 percentage is only the solid content, so 15 percentage of 150, or I can write it as 0.15 times 150, so which will be nothing but it should be 7.5. Oh, sorry, 22.5 kg of solid content. Now, 8 percentage concentration is the favorable condition. So that influent which has 8 kg. So 8 kg is there in 100 kg of your influent. So for 22.5 kg, how much it is going to be? So again, just a cross multiplication. So 22.5 times 100 by 8. 2.81, oh sorry, into, so times 100, right? So 281.25 kg. So this is for one particular day. So the entire digester working volume is for, because the HRT, that is the residence time, is actually for 50 days, right? So then the digester volume will be, digester working volume, so will be 281.25 times 50. So it will be 14,062.5 kg. So this is the, actually this is the amount of, this is the amount. So now we are supposed to convert that into the volume. So since that slurry that you're going to actually feed into the biogas digester contains 92 percentage water, so what we can say is that the density of that slurry as such, we can take it, we can assume it as density as the of the water. So both the densities will be same. So with keeping that in mind, this will be in terms of, so you can write this as digester digester working volume as 14,062.5 by 1000. So that will be around 14.0625 meter cube. So here we are, since as we said previously, in case of this biological conversion routes for biogas production, the total solid content that is going to be present in your slurry is only 8 percentage, and the rest 92 percentage is going to be water. So we can typically take the density of that slurry as the density of water, and based on that we can calculate the working volume as 14.0625 meter cube. Is it okay? Yeah, so we have something so called as a geometrical assumption. So this basically is a sort of like, it's an assumption for the construction of the biogas plant, where they consider that VGST, that is the volume of the gas storage volume, plus the volume of the digester, or you can say VD, is going to occupy 0.80 times of your total volume of the reactor, the biogas reactor. So here I have specifically written, do we have VD here? Okay, we don't have. So so the digester's working volume, we take it, so the one that we get, the digester working volume, is nothing but the volume of the digester chamber plus the gas storage unit. So that is 14.0625 is nothing but it is 0.80 times volume of the digestion chamber. So that volume is going to be 14.0625 by zero point 0.8. How much is that? 17.57 meter cube. Just a second. I'll take this part. I'll just cut it. Yeah. So, is any discrepancies with the answer? Okay. So, was there any other query that you were? Oh, okay. So, I am. So, okay. So, yeah. So let me just note that question down, and I will solve it myself because I have not checked that answer to that question, or I have not solved that particular assignment question, whatever is there. So Once I do that, then I will let you know next week. I am just noting it down. Hmm. Hmm. Okay, so what is so you just mean to say that I need to continue solving it using this formulas as well, right? Mm-hmm. Okay. Yeah, please do that and then yeah, yeah, yeah. So I'm also noting it down. So let me just check it once. Hmm, hmm, hmm. Hmm, hmm. Oh, hmm, hmm, hmm. Okay. Okay. So let me yes. Okay. So for this question, what is the answer then we are getting like. Yes. I'm not asking for the dimension. So that will be, I actually, since it's just like a practice session, so I kept that as a separate question wherein I'm asking for both. I just want here the volume of the digestion chamber. So, yeah. So, as per that, is the answer fine? Yeah, this is not the assignment question. Yeah, as I said, I am not supposed to discuss the exact question or the assignment in the live interaction session. So, yes, yes. Hmm. Yeah, 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 yeah. Okay, okay, okay. I will look up after that. So, hmm, yes. Yeah, so you please check it out and then we will see in the next week. I will also, if possible, then I'm not sure because when I will be uploading the PPT because whether it is after the date or before the date. So if it is after the date, then I will try solving it and then posting. If it is before the date, then we will take it in the next class as a first problem before discussing other questions related to week 7. Yes. Mm. Yeah. Mm-hmm. It will be very similar to what you actually solve in the assignments. Mostly, yes. Okay. Yeah, yeah, yeah. So since mm, 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 yeah. Okay, okay, okay. Okay. Yeah. Okay. Okay, okay, okay. So, if you want like that kind of a split up, I would better suggest to post that question in the forum. So yeah, it is. Yeah. So this question I have to. Yeah, I am not very sure. So as okay, yeah, yes. Actually, I'm not sure about this part. So I would suggest you to actually ask the NPTEL, not even in the Q&A forum, but you should better mail to the NPTEL team, mm, not this particular the course forum, but then the main NPTEL team. If you basically mail them, then they would be probably okay. Yeah, yeah. So I'm not very sure about this whether it will be eligible for your college. I have to look up after that. As I said, I haven't solved that particular question, so I will let you know in the next week's session. Okay. So so for this question, we have around 10 minutes left. So let's try to do this one question. Actually, we have another two more lined up, but that's fine. Let's try to do this question wherein here same similar pattern, but just that you need to actually calculate even the dimensions of the digester chamber. So wherein you need to calculate the V1, that is your top head, bottom head, all the parameters whatever is there in this orange the box that you see. No, no, next week it will be on 9th March. Oh, tomorrow I'm not sure about the next. There is one more also who is conducting the live interaction session, right? So you have two every Sunday and Monday. So I'm not sure about that Monday one. Mine will be next week. I mean, in the on 9th of March. Oh. So same process, but then you need to calculate D, V1, V2, V3, R1, R2, H1, H2, and S1 and S2. So it's typically more of a place where you need to like. So here we have calculated B. So with this V, we are supposed to calculate D. So once you get D, it's all just with the equation. So if you know D, then you can get V1, V2, V3, R1, R2, H1, H2, S and D. So it's just that if you calculate D, you can get almost all the parameters. So instead of solving this question, I will calculate D here itself. So D is nothing but it is, what is the formula? 1.3078 times V power 1 by 3. So V power, so D is nothing but 1.3078. So this is not right. So D will be around 2.59 meter. So once you now have D, then volume of top head, bottom head, chamber, I mean the middle section, that is your cylindrical part, H1, H2, R1, R2, S1, S2, all these things can be calculated. So it's just that you need to use the formula to calculate the dimensions of the digester. So this I'm just going to leave it for solving, because it's just about you need to plug in the values to calculate the answers. So last week we didn't discuss on one particular question, so which I want to just share it here. So this is the last question for today. So in a laboratory of wherein you have 100 gram of plastic waste, you are pyrolyzing that in a batch reactor which is weighing approximately around 900 grams. The weight of the oil that is going to get collected is 60 grams, and the final weight of the reactor is 1150 grams. Calculate the gas of the yield, calculate the yield of the gas, liquid and solid fractions. It's a simple question. So you have the batch reactor which is weighing 900 grams, you have 100 gram plastic waste, and then the oil that is going to come out from this pyrolysis reactor is 60 grams, and then the final weight of the reactor is 1150. So you are supposed to calculate the yield fraction. So for weight of the oil is very simple. So as such, when I say here yield, what it actually represents, yield of gas. So it should be like, it's just a fraction. So what should I divide the weight of the oil collected with? Should I need to divide it with the reactor's weight or the weight of the waste plastic? Weight of the waste. So you are calculating yield with respect to the amount of waste material or the input that you are going to give. So this divided by weight of waste plastic. So this is nothing but 60 by 100. So that is 0.6. Then you have to calculate yield of liquid. So how do we calculate that? Oh, sorry. This is the weight of oil. So weight of solid you have to calculate. So oil is the liquid, so that you can get as 0.6. So weight of solid, initial weight of oil. So that will be around 25.25. And so after this, you have the weight of, sorry, yield of gas. So which will be nothing but 100 minus your 60 and minus 25. So that is 15, right? 0.15. So I think there was some mistake with the respect to this one. So apologies for that. And so this is again, it was a simple question. So there is this question which is left out. So I would probably suggest everyone to actually, do this, take it as a task because it's something very similar to your assignment question. So that's the reason I gave it as a separate problem also. So yeah. So that's all for today. We have two questions. I think we will do it in the next class. So let me stop presenting. Any doubts related to what we have discussed today? I have noted down the assignment question, so I'll solve it and I'll respond to it as soon as possible. Apart from that, so I will. Was it not available? Okay, I'll just type it in the chat box. So I've typed it in the chat box. So if you have any queries, then please email me. I will try to reply to it as soon as possible. So let me conclude the session for today. So thank you everyone for joining. So we have actually covered exactly 2 hours of our session. So let's meet on 9th March for week 7 live interaction session. And I thank for Professor Prasanajit Mondal and the NPTEL team for providing me with this opportunity for, to meet you guys or on this Sunday afternoon. So let's meet next week. Till then, bye. Yeah, thank you, sir. Thank you.